How can we measure, characterize auditory filters? Critical bands, the experiment of Fletcher 1940. Tone in band pass noise centered at same frequency. Find threshold of a tone of a function of bandwidth of noise. Find threshold of a tone as a function of bandwidth of noise. Okay. Uh, Bandwidth of noise. Yeah, it shows up that if you have masking noise bandwidth up to 400 Hertz, then the threshold increases with increasing bandwidth. The signal threshold increases. It's for a 2 kilohertz tone. But then after when the masking noise bandwidth is more than 400 hertz, then the threshold will be the same, constant, about maybe 75 dB SPL. So it's called those 400 hertz or a little bit before 380 or what it is called the critical bandwidth, about 400 hertz. Yeah. So threshold remains constant with increasing bandwidth after those 400 hertz. Auditory filters an increasing noise band. If the noise band is narrower than the critical FCB, then if the noise band is smaller than the delta FCB, the critical bandwidth, I will think it is. Then there is then the threshold will increase with the bandwidth. And if the noise bandwidth is bigger than the critical bandwidth, then there's a constant threshold. Yeah. Yes, we have here bandwidth. Bandwidth is yeah. Okay, we can estimate bandwidth of auditory filters from critical band physical threshold test problems. Estimate of critical bandwidth is not very precise, and it doesn't tell us the shape of the auditory filters. Only the FCB. Okay. Yeah. Yips. Bandwidth is less than the bandwidth is less than yeah. Different approach, not noise. So we have a noise in front, and we have a noise on both sides of this F0, this pure tone, and the mask threshold as a function of the knots with delta F. So we have this Gaussian. It has auditory filter, and this part of the noise is inside the filter, and thus it contributes to the masking of the pure tone. When the noise is inside the auditory filter, it contributes to the masking of pure tone. So if the noise are far away from the auditory filter, there is no masking. Yeah. So the bigger the knots width of the in hertz in delta F, the bigger it is, then the tone threshold is decreasing, of course. It's very narrow. You need if the knot width is very narrow, you need a big tone threshold. Then there are some power spectrum model assumes that mask threshold is proportional to the power of the noise of the filter output. Yeah. That would say the tone must have some minimum SNR within filter. We have a test tone and we have a proportional constant, and we dine with an integral from 0 to infinity. We integrate over the frequencies, and the integrand is called masker power at output. Masker power at output of auditory filters. It is auditory filter response times the noise of masker, power of noise masker. Okay, so yeah, there's a probability between the test tone power at threshold and the masker power at output of auditory filter. Assume masker is white noise with power density constant 0 and filtered by an ideal stop notch filter with a notch width of 2 times delta F. Then the test tone power is a threshold PS is K constant times in 0 times an N. Yeah, it belongs of two contributes. It's masking by lower pass noise plus masking by upper noise band. From the lower band, masking by lower band noise is from frequency from 0 up to f0 minus delta f, and then after from f0 plus 0 plus delta f to infinity. Yeah, yeah, okay. And we remember it where the noise is shares area with the auditory filters. There are some masking going on. Then we have a equivalent rectangular bandwidth (ERB). ERB is a bandwidth of rectangular filter with same output power as auditory filter. It has a bandwidth. It has a bandwidth. This ERB bandwidth and the area of the rectangular with this bandwidth ERB bandwidth times the V auditory filter maximum is the same as the area under the curve, the whole curve. Yeah. So an ERB varies with frequency, where F is some 24.7 times 4 times parentheses 4.37 times F plus 1. And there are also some Bach's transformations. It's about how many what's called critical bands is needed to cover the whole range, frequency range. It's a little bit. I'm not quite clear about that. Yeah. Level dependence of auditory filters. At medium levels, filters are roughly symmetric on linear frequency scale. Linear filter approximation holds as medium levels. At high levels, filters are highly asymmetric. The higher levels, test tone, if masker level is a parameter. Masker level is a parameter. Then, yes, and we have a test tone at 1 kilohertz. Then the output level, there's a there's a offspread. Yeah, the levels, frequency levels at to the left, less than 1 kilohertz. The level output level is bigger than the decreasing less than when the what's called when the frequencies are more than 1 kilohertz. Yeah. So yes. Masking level, a frequency, tone, yeah, is normal versus hearing loss. Impaired broader auditory filters and reduced frequency selectivity and difficult to segregate sounds, speech and noise. And then it shows up that notch noise minimizes all frequency listening effects. Yes. So you can say the area, yeah, it's the best way. Putting all together, resulting results from masking experiments, auditory results from masking experiments, auditory filters, excitation patterns, and they are all related. How can we explain this? Auditory filters versus excitation pattern. You have some let's say we have 1 kilohertz tone activates many auditory filters. And one tone activates many auditory filters. Yeah. So you have a frequency on the first axis and auditory filters on the second axis, the relative gain. So you draw all those auditory filters with different center frequencies. Some center frequencies are smaller than 1000 hertz and some are bigger. And then you take this straight line upwards and you find out where they intersect with the different auditory filters, and then you make from that you draw the excitation pattern, excitation pattern curve. So you if you find this place where 1 kilohertz tone it intersects with the 500 hertz auditory filter, 500 hertz center frequency auditory filter, then it's a point. You have a value. It has a relative attenuation excitation level, and then you put this value, for instance, 40 dBs to the center frequency of, in this example, 500, and then 750 and 1000 and 1250, 1750, and so on. Okay. Changes increase with increased level. Now it comes. You have first auditory filters at 1 kilohertz. Auditory filters at 1 kilohertz. You have an increasing level. Yes, and so the input of the tone swept in frequency, output at one point along membrane. A 1 kilohertz tone activates many auditory filters. Yeah. Auditory filters broaden on the low frequency side. Yeah. On the low frequency side, they broaden. Okay. How? Yeah. And how about the excitation pattern? Still have this 1 kilohertz tone input. Now the input of a tone is fixed in frequency. It's not just a special at a certain point on the basilar membrane, but now the tone is fixed. And then output at different points along basilar membrane. At the auditory filters, it was different frequencies at one point on the membrane, and the excitation is one tone fixed frequency at different along the whole basilar membrane. Excitation patterns broaden on the high frequency side, as I talked about before. Thank you. That was part 2.